Welcome to section 1.9. We're talking about inverse functions. So let f and g be two functions so that f of g of x equals x for every x in the domain of g, and for g of f of x for every x in the domain of f. We'll get to that in a little bit. Now, when we write them as an inverse function, there's notation we're going to use. F to the negative first, that's read as f inverse. So when we're testing to see if functions are inverses, when we use the composite function, so for f of g of x, it has to equal x, and for g of f of x, it has to equal x. And it's the same for inverse functions. F of f inverse of x has to equal x, and f inverse of f of x has to equal x. I have an old notation and new notation. So what we're doing is that the domain of f must be equal to the range of f inverse. And the range of f must be equal to the domain of f inverse. When we're finding inverses, we're switching the inputs and outputs. That's really what we're doing. We're switching the inputs and outputs. Now, usually we'll be changing and coming up with a new rule to change the inputs, the outputs, and vice versa. So for problem number 1, we're going to find the inverse of the set of points. Now for the inverse, so for f inverse of x, all we're going to do is switch those inputs and outputs. So our first ordered pair, instead of being 2, 3, we flip them. 3, 2. 3, 5 is going to become 5, 3. We switch the inputs and outputs. 4, 7 becomes 7, 4. 5, 6 becomes 6, 5. We're literally just taking the input and making it output and vice versa. So finding the inverse of the function is given to us, but we can just use our ordered pairs. So f inverse of x is going to equal, so we're going to switch them. 5, 1, 6, 2, 7, 3, and it becomes 8, 4. Next, we're going to talk about finding the inverse for f of x equals 5x. When finding the inverse, what I do is I switch f of x with y equals 5x. I put it in a more familiar form. Now with inverses, we're switching the inputs and outputs. So we're going to replace y with x and x with y. So it's going to become, so we had y equals 5x, so now it's going to become x equals 5y. So we switch the x and the y, and now we're going to solve for y. To get y by itself, we divide both sides by 5. So y equals x over 5. Since we were given this in function notation, we're going to put our answer in function notation. So our inverse would be f inverse of x equals x over 5. That's our inverse function. Now it says verify. To verify, f of f inverse of x has to equal x, and f inverse of f of x has to also equal x. So we're going to find f of f inverse so it's going to be f of x over 5. So it's going to be 5 times x over 5. The 5's cancel, so we get x. That worked. And then it's going to be f inverse of f of x. So it's going to be f inverse, so it's going to be f inverse of 5x. So instead of writing x over 5, it's going to be 5x over 5. The 5's cancel, so we get x. That's how we verify their inverses. And you can see we're using those composite functions from 1.8 again. That's why we had to do 1.8 before we could talk about inverse functions. So now we're just verifying that f and g are inverses. So we're going to find f of g of x and make sure that it equals x. So it's going to be f of x plus 3 over 2. Now I want to see your work for these. Don't just say it magically equals x. Because I might give you, to verify, I might say, all right, are these functions inverses? And it might not be. So that's why we want to make sure we check. So the function f at, sorry, you did that already? So it's going to be the function f, which is 2, leaving some space, minus 3, and in that space it's going to be x plus 3 over 2. I'm also testing your order of operations here. When we multiply, the 2's cancel, so we're left with x plus 3 minus 3, which equals x. So we're good. And now we go the opposite way, make sure it works both ways, g of f of x. So it's going to be g of 2x minus 3. So it's going to be x plus 3, so leave that blank, plus 3 over 2. Using our order of operations to get rid of the grouping symbols, we get 2x minus 3 plus 3 over 2. So it's going to be 2x over 2, which is x. So there we go. We just verified that they're inverses because they both equal x. Let's do some more of those. Some more verification problems. So now for problem number 5, we're verifying that f and h are inverses, so we're going to find f of h of x first. So it's going to be f of 5 over x plus 2. So it's going to be 5 over x plus 2, and then we're subtracting 2 at the end. Now it looks messy, and it is. But what's nice is that the 2's cancel, so it's 5 over x. We don't divide fractions, we multiply by the reciprocal, so it's 5 times x over 5. The 5's cancel, so we're left with x. There we go. We just verified that they're inverses for that part, and let's go the opposite way. H of f of x. So it's going to be h of 5 over x minus 2. So it's going to be 5 over, once again, this is pretty ugly, 5 over x minus 2, and at the end we're going to be adding 2. Work with the fractions first. We don't divide, we multiply by the reciprocal, so it's 5 times x minus 2 over 5. Order of operations, we multiply first, and then plus 2. So the 5's cancel, so we're left with x minus 2 plus 2, which gives us x. There we go. They are inverses for sure. Number 6, same thing. F of g of x has to equal x. So for f of g of x, we're going to have f of the cube root of x plus 1 over 2. So it's 2 times. Leave that blank. Minus 1, and remember we're substituting the cube root of x plus 1 over 2. Order of operations, we're taking the exponent first. When we cube a cube root, they undo each other, so we're left with 2 times x plus 1 over 2 minus 1. We multiply, the 2's cancel. We're left with x plus 1 minus 1, which gives us x. Good on the first part. Let's do the other side. G of f of x. So the function g of 2x cubed minus 1. So now it's going to be the cube root of 2x cubed minus 1, and then plus 1 over 2. We're working inside that cube root first. Combine your like terms in the numerator, you get 2x cubed over 2. Now the 2's cancel, so you're left with the cube root of x cubed, which gives you x. You really want to watch your order of operations here for these problems. Some people just kind of start canceling things crazily, and they're breaking the rules of order of operations. You cannot do that. You must do them in a certain order. Now when we graph our inverses, once again, we can switch the inputs and outputs. And I'll show you what happens when we graph these. So if we graph f of x equals 2x minus 3. So 2x minus 3, the slope is 2, and the y-intercept is at 0, negative 3. So 0, negative 3, up 2 over 1. So here is our function for f of x. Now for g of x, that's also the same as 1/2 x plus 3 halves. So I'm going to have my y-intercept. I'm going to change my color here, like a blue. And we're going to be at 3 halves. And now we're going to go up 1 and over 2. So we're kind of going up 1, we're in between, over 2, up 1 over 2, up 1 over 2, up 1 to the right 2. We can also go down 1 and to the left 2, down 1 and to the left 2, down 1 to the left 2. A little bit messy to graph, but that's kind of what's going to happen sometimes. So there is our function of g of x. Now, what's going to happen here is that these two lines are going to be the reflection along this line, y equals x. So if you were to hold a mirror along this line, y equals x, you would see that you would get the other graph. It's a reflection along the line y equals x. That's what inverses always are. Now, not only that with inverses, but if we look at some points, I can see for f of x, I have some points there. I have the point -2, -7 is on f of x. -1, -5 is on f of x. And I'm getting these right from the graph. 0, -3, 1, -1. Now, if you look at g of x, some points that are on g of x are -7, -2 is on g of x. -5, -1 is on g of x. -3, 0 is on g of x. -1, 1 is on g of x. You see how we're just switching those inputs and outputs? They're inverses of each other. The input and the output are flipped. The input becomes the output becomes the input. Let's do a couple more on the next page. I'm going to sketch the inverse of the functions. So what we want to do is we want to find out the points that are on the original graph. So the points on there are going to be -1, 1, -2, 2, -3, 1, and -4, -2. So now the points on my new graph, we're going to just switch them around. 1, -1. 2, -2. 1, -3, -2, -4. So we go to 1, -1, there's a point. 2, -2. 1, -3. And -2, -4. And here is our graph of the inverse. And that would be the reflection along this line, y equals x. You see how they kind of match up? Same thing for problem number 9. Some points on that graph. -2, 4. -1, 1. 0, 0. 1, 1, 2, 4. So when we take the inverse of those, 4, -2. 1, -1. 0, 0. 1, 1. 4, 2. 4, 2. 1, 1. 0, 0. And there is our inverse. And that's the reflection along this line, y equals x. Next one's a little bit trickier, the points on there. I know it doesn't show that it's on there, but there's another point on here that's at 2, 8. There's a point here at 1, 1. There's a point here at 0, 0. Negative 1, 1. And then another point would be at negative 2, negative 8. So when we switch those around, we'd have a point at 8, 2. We'd have a point at 1, 1. We'd have a point at 0, 0. We'd have a point at 1, negative 1, and a point at, that's at negative 1, negative 1. Negative 1, negative 1, and negative 8, negative 2. So we're at negative 8, we'd be at negative 2. Back here. Negative 1, 1. 0, 0. 1, 1. 8, 2. So about there. So our inverse would look, didn't go far enough, would look like this. You know, it's kind of tight there, but it is the reflection along that line of y equals x. We're going to stop there. I'll see you in the next video.